Well, thanks the organizer, Taro, for organizing this wonderful workshop. It's great pleasure to be here again, seeing all the old friends. Well, here's the motivation for this talk. This classical paper by Rayo and Eugene, 91. I want to prepare my talk. I just realized 91 is a time three of us overlap exactly at UPenn. And I think Rayo's office is next to me, and Eugene's office is on the other side of the buildings. So it has been 30 years, exactly the same time, around the same time we were together. And that time we talked about the things we talked the most is job opportunities. What is the next job? So I didn't realize now we're talking about the, birthday conference, right? The time flies. All right, so don't ask me what stratified manifold, symplectic manifold is. So I assume everybody knows J inverse 0 divided by G is a symplectic reduction, and if it's nice enough, and that is the usual smooth manifold. And if it's bad, then they prove that this is a stratified manifold. So what I'm going to do is, try to make sense what the question is. Only I talk about what a J inverse 0 is. So revisit what the paper and try to see, this is one goal is to try to see if there's a way to recover what Rayo and Eugene did 30 years ago using derived differential geometry. So but this is the ultimate goal, but I don't know. It's just the first step is to see what is the J inverse 0 is. And so J is a momentum map. And so try to see if this is a smooth object. One thing we notice what J is this J inverse 0 is just fiber product, right? Fiber product with this point going to 0 and this. So the general talk, what I'm going to do today is try to make sense what is a fiber product. So this for arbitrary X, Y, Z to make sense of this. Is there any way to make sense to be smooth? So the approach of this approach is try to enlarge the category of a usual smooth manifold. The usual smooth manifold is a category, the objects of manifold, the map are just smooth maps. And is there any way to enlarge this category so that we can talk about a fiber product? So that's the idea. More specifically, we're going to prove the theorem. Basically, the category derived manifold is a category of fiber object, CFO. So most of the time, my talk today is try to explain what is the derived manifold in the sense we're trying to come up with the definition. It's a curved infinite algebra curve. So let me just make a remark over here. Everything I'm talking about, just smooth manifold. I grew up as geometer, differential geometer. So I trained as a smooth manifold. And that's what I'm not talking about the variety. I'm not talking about the algebra variety. So everything is a smooth infinity. And what is the fiber product? In the usual sense, this is just definition, right? The fiber product, which is just topologically, it's just topological space in general, but it's not a manifold. Unless, if one of the map is submersion, that's what we learned when we were graduate student, and then there's a smooth manifold. Actually, you can have a weaker condition. You just need a transversal to the diagonal. But if one map is a submersion, it's a smooth. But in general, it's not smooth. It's only topological. Only is the topological space. All right, so that's what the and now the fiber product, in fact, not only covers J inverse 0, also covers, for instance, intersections. And this is a people normally interested in if if you have two submanifold, the intersection of a two submanifold, you can think of it just fiber product, right? And basically the just inclusion. So, and that takes care of what is the intersection, and also takes care of a critical locus. And that's people in the flow homology, that Chris talk, I think, I don't know if he touched this. This is a very standard critical set of Lagrangian with zero sections. So this is just, you can consider just the section of two Lagrangian intersection. One is zero section, and the other one is graph of DF. And in general, again, this is a very bad space, the only topological space. It's not smooth manifold. And can you make sense of those to be smooth in some sense? So, and those includes all those basic geometric objects we're interested in. Try to make sense of what smooth means. All right. So now a bit of a history. I'm very bad in history, so do not. so may overlook of a lot of people's name over here. Actually, from algebra geometry point of view, probably very beginning around before even Kepler-North started looking at the DG scheme, all those things. But from differential geometric point of view, and like Eugene yesterday mentioned, Spivak was the first one. Tried to adapt all the algebra geometry to the symphony category, in the symphony sense. So I think he did, but everything is infinite category. So, and those are list name. And yesterday, I think Eugene talked about symphony ring, right? Not derived, but it's the same purpose. You want to do something, the exactly same idea. So you want something to, like a calculus, right? Got done calculus for something very bad. Geometry. It's the same idea, right? And what you call, I mean, derived, you can call anything could be derived. So what you like to do. So the same idea. So what the our idea is just try to avoid infinite category and use something very down to earth. So what is really the normally when you go to infinite category, that's all the algebra geometry you do. And for people like me, grow up in differential geometry, it's very hard to put hands on infinite category. If you really want to say, if I want to do simple reduction, J inverse 0 divided by G, and this is so here basically our point of view is to try to put something really basic to put hands on. And by the end of the talk, I gave you examples. Basically, you can really look at how to do fiber product. All right. So that's the idea. That's the idea. Any questions? Oh, sorry. Yeah, that's crash course. That's what I'm going to do. so this is here. Yeah. So before I talk about it, let me mention a little bit the category of fiber objects, CFO, and I just noticed this is related to quite a lot of people from Cornell, right? I noticed. So there's a lot of people, Braun, but he is from Cornell. Oh, okay. Did I ever meet him? Did I ever meet him? Because we used. Oh, right, right. Because not in the symphony, not in the joint seminars. He never showed up. Because I was looking at it like Braun, I tried to figure out which one. Kansas, they said Cornell. I didn't even realize. But it's amazing. But this is like a CFO. Very few people, I think, it's notice this. This is a CFO. So category, because a lot of people use modal category or those. It's just very complicated. Basically, the idea we're trying to use here to promote this terminology, which is invented by Braun from Cornell, and he basically. What is a category fiber object? So it is just a category. You have two relations. One is a fibration. One is a weak equivalence. So if you're a geometer, I'm trying to talk about it from my own experience. To think about what the fibration would. So if you're a geometer, you know what submersion is, right? Single fibration is just submersion. That's exactly just submersion. You think about it. And weak equivalence is just quasi-isomorphism, like a map between two things, and the optical margin is the same. Exactly, that's what you want to think about it. If it's geometry, so because I always scared of an infinite category, also sheaves, because I grew up without the learning all those terminology, so I got scared. So anyway, so those are the axioms. So you have two fibration and also weak equivalence, and satisfy all the condition here. What is the, let me just, it's just a little bit technical, but what I want to point out is just last one is the most important. What is 2 out of 3? If you have, let's say, X and Y, Z, those are 3 objects. You see. Those, yeah, I will give you next slide. So can I just talk about the first axiom? What it means 2 out of 3. 2 out of means 3 is have 3 objects and 2 morphisms, G, and this composition FG. So it means if any 2 of those weak equivalent, and then the other one has to be weak equivalent. So that just means 2 out of 3. So you have a composition if 2 of them weaker. So that weak equivalent you satisfy this condition. And the isomorphism fibration, you can talk pullback. Like if it's submersion, you can talk pullback, right? I mean, always submersion. You think about it. Exactly. If you're geometer, you can see. And trivial fibration means fibration, which is also weak equivalent, quasi-isomorphic. And final object, you have like a 1 point or something. So final object. The last one is the most important thing. So basically, you can factorize the diagonal map by replace something much bigger, and this is weak equivalent. It's a trivial fibration, basically weak equivalence, and also it's a fibration. So it's much bigger, and then this guy is some fibration. So if you're familiar with modal equivalence, this is very similar to kind of a loop modal equivalence.
Subcategories, should we think about the same object with different
relation. So you ask the examples. This is examples here. So the model category is, but I deleted last night. This one is, I think, it's most interesting example. People just coaching category.
C, which is just category of manifolds and smooth maps. That's not going to be this.
No. That's exactly the point. If you look at the category of the smooth map and object are the smooth manifolds, and the map is a smooth map, it's not a CFO because you cannot factorize. This fails. What is this one? This one's a fails. This one fails. The diagonal you cannot factorize.
So here should we think about the paths and the map is just the initial.
No, PX is just notation. So PX is, PX is in your mind, you can think of like a path space, but it's just something, let's say Y notation called path space. But this one is you can weak equivalent, which is a weak equivalent to this, and then this is also fibration. But then this guy is exactly become. It fails. So you cannot, given diagonal map, you cannot replace this X equivalent. Well, what is a equivalent, weak equivalent for 2 smooth manifold? The only thing you can put is a diffeomorphism, right? There's no need, there's no room to play. What is a weak equivalent? 2 smooth manifold, what are the weak equivalent? I mean, if you only require smooth map to be morphism, the only is diffeomorphism. So there's no way to get a PX. So the point here we try to do is okay, so you need enlarge of smooth manifold to be a little bit larger. It's not so bad, graded manifold, DG manifold, a little bound of infinite algebra. It's not so bad, but you don't have to talk about sheaf. And you don't have to talk about infinite category or these things. Yeah. So, but a smooth manifold does not work, the usual category. Yeah. So, and this is one of the examples. The weak equivalence is quasi-isomorphism, and the fibration is just these surjective chain maps. And this is CFO. And now, so what actually in Brown's paper, he gave outline. What do you do is if you have those axioms, so which is long axiom, in fact, is the most important one. As I said, just diagonal map. You can factorize. Once you do this, any morphism in this category, you can factor. You can just replace by p, and basically, if you have x, q, y, any map, any morphism, you can replace by a bigger one, whatever, and just like loop. This guy is a fibration, but this guy normally is fibration, also weak equivalence, like a equivalent. And then also you have a sections. So, and therefore you can replace x by this p, which is a fibration. And then you can talk about the homotopy fiber product. So in fact, with this, he gave in his paper, everything is our paper. He talked about it. Everything makes sense in the CFO up to weak equivalence, up to this weak equivalence. And you can talk about fiber product. What you do is, if you have x to z, y, you just replace this morphism by a much larger space p. No, it's just another object, right? Which is weak equivalent to y, also fibration, right? And then this guy is submersion now. You think of this submersion, fibration, submersion, and then you can take a fiber product. What he proved, so this will be the homotopy fiber product. What you can, I think in the paper, he justified this is what defined. This is up to weak equivalence. All those, that's not independent what choice. What is it? So this is CFO. So with this, well, there's a fancy way of saying if you have CFO, you can normally when you get a weak equivalence, you take a localization, you get infinite. You have got infinite category. In this case, it basically is give you a model for that infinite category. It's a lot easier to talk about. So next thing, I'm going to talk about what is the infinite one algebra. I prepared this last night in a rush, so if some mistake, don't blame me because there are. So let me see. Hopefully, there's not too much mistake. So let's start with linear algebra. And what is let's say V is a graded vector space, and you have a degree Vn. So each this component have a degree n, right? And so when I write a V shifted 1 means D is a map of a degree 1. If I have this means putting shifted 1 means this map a degree 1. So on. And the cochain complex means have this map and D squared with it. And that's just the usual notation. So this is a standard. What is DGLA? Differential graded Lie algebra. What DGLA? Now you have to allow yourself to make sense of a Z-graded vector space instead of usual vector space. Usual vector space and give you Lie algebra, and now you need a Z-graded vector space, and now you have a D, which is the degree 1 degree 1 map. That's what, and a bibracket, and satisfy those conditions. That's right. And graded Jacobi and then D is derivation, right? So, and this is graded Lie algebra. So what is the infinite algebra? It's just extension of this notation to much more operations. So what is the operation here? Instead, well, here, I'll be careful. I need a curved infinite algebra. So curved infinite algebra. So you start with a Z-graded vector space, and now I have a bunch of a map with degree 2 minus n. So including lambda 0. So lambda 0, so if I look at the lambda 0 will be just lambda 0 will be, in fact, just element in V. If I put in 0 there, should be degree 2 elements or what? Yeah. And so And degree, so lambda 1 is just V2V, just like a differential there. And lambda 2 is a bracket, and so on. You have a bunch of it. And then you have all the graded Jacobi identity, which is the extension of this other identity over here. Now, what is, so in particular, so here's a few relations, the first beginning of few relations. Lambda 0, so lambda 0 is, you have, lambda 0 is, so lambda 0 is V2, and lambda 1 is V2V degree 1 map, and lambda 2 is V wedge 2 schizommetric to V, and so on. And this is degree 0 map. And so if you look at the first few relation, so lambda 0 is one element, make a D has to be 0. Lambda 1, think of lambda 1 just D differential. And then this identity means this is if lambda 0 equal to 0, this is called D lambda 1 is twisted differential. Because if this guy lambda 0 is 0, that means lambda 1 is square is 0. That's just a Cauchy complex. And so, and this is a graded Jacobi identity up to homotopy lambda 3, up to lambda 3. I think so. Is that, no, even not. This relation is like a D. If you think of lambda 0 equals 0, and this just means lambda 2 is a bracket. So this just means lambda 1 is differential with a bracket. So, and so on. So a curved infinite algebra with the first lambda 0 equal to 0 is just DGOA. So curved infinite, that's a special case. And so when you talk about morphism infinite algebra, the strict one is you want to preserve all the bracket. That's the naive way, but it's bad notation. It's not the right morphism. It's not right morphisms. And the correct morphism would be, so what is the L infinity one algebra? Infinity one algebra is you need to shift the degree. You need to shift the degree. So infinite algebra is, this is annoying here. I do not know how to, okay. Well, you just have instead of schizommetric, you got a symmetric. It's the same thing. And then the degree is instead degree of 2 minus n is a degree 1. So a bunch of this map satisfies same kind of relations. So this is what you really need to remember is that V is the infinite algebra, same thing shifted by 1 is the infinite 1 algebra. So if you, in other words, infinite 1 algebra is the same thing by shift minus 1 is the curved infinite algebra. Curved is means this guy, you do have the first one here. Usual infinite algebra, you only start with lambda 1, which is just a map, degree 1 map. And then lambda 2 is a bracket, and lambda 3 is a 3 bracket, and so on. But here you have a lambda 0. Yeah, so you need a curved. Well, another way of looking at this is using co-derivative. Later on, I will tell you another way of looking at it, actually using DG point of view. So giving a graded vector space, look at symmetric. This is a linear algebra again. Look at symmetric algebra, which is not algebra. You have a co-algebra. You have a co-map. Basically, this is up to sign, right? So this is a co-algebra map. So what is a compact way to look at it? What is the L infinity 1 algebra? Is you have a degree 1 map of SW to SW, degree 1 map, which is a co-derivation. That's the compact way. What a co-derivation means, this map commuting, and square equal to 0. So this is exactly a compact way of L infinity 1 algebra. If you read the literature, and that's what the literature says. But I do not like this definition because co-derivation is hard to work with as geometry. In fact, I like to take it, I would suggest using the do map. I will show you the next definition in the next 2 slides using the do. When you take the do map, and then you become co-derivation, become derivation, which is just a vector field. That's just vector derivation, vector field. So as geometry, we use all the vector field all the times. But the usual literature, when they talk about infinite algebra, you use co-derivation, is W is normally infinite dimensional, like vector fields, like when you do formality or those. So you do not have a do. Do does not make sense. But what I'm talking about, all the W is just vector space, finite dimensional vector space. So either you using the SW or using its do, it's the same thing. There's no ambiguity because the W is a finite dimensional vector space. So if you're using do, that just means you take the do map, co-derivation become derivation. And square equals 0. So I'm going to show you the next one, how to look at later on. But this is just usual definition. Just for people familiar with the literature, that's what you normally see. All right. Now, how to see those maps? Compact wave, seeing all those maps, it's very easy to see now. What is that map? Is because in this case, co-derivation is generated by this map. It's this component SKW for all the k. So you just include this map to SW, and Q is a degree 1 map, and then look at a projection to the first component W, and then you get a bunch of a map lambda k, starting with k equals 0. And that's the high bracket. This is the high bracket. And that's how you can, and then the Q square equals 0, exactly just you write down the definition, you will see all the bracket, the Jacobi identities, all the Jacobi identities.
So you write symmetric algebra, you mean graded symmetric algebra.
Graded symmetric algebra. When you do the symmetric, you have to, the only thing you have to remember is the sign. You want to switch, you have to use all the Kouzou sign. That's all you need to remember. But usual things, you just need a little bit changing your mind. I think at beginning, I hate all the sign, but now I feel comfortable. You don't need to write sign anymore. You just write plus or minus because you just follow the rules. Kouzou rules, so whenever switch, you need to remember. And that's all you need. So I just try to convince you guys, you just need a little bit, then you're fine. So really beginning, I was very confused with all the sign. So what the morphism is, and now for this way to see what the morphism is a lot easier to see just the morphism core algebra, the morphism core algebra. So if infinite curved infinite algebra is just morphism, let's say, because I have at least just a map between SV to SW, because SV is a core algebra, and this is a DG core algebra, right? You have a Q. So you want this map to be DG core algebra map. If you write down the co-derivation relation, you will see a bunch of these maps, because so this will be determined by, you can see you have this is a core algebra map, SV to SW, and now you encode to SV, and then you project down W. So you have a bunch of this map. And this is will be the morphism of L infinity 1 algebra. So instead of one map, and you have a bunch of maps now. Any questions? And again, I would recommend for finite dimensional vector space WV, you can look at do, which is a lot easier. The do map is just the DG algebra map. If you like a DG algebra map, you can see commuting with Q, and basically you will see those bunch of a map. Just read the Taylor coefficients. And now what is the derived manifolds? So here's a definition. If you feel comfortable with the infinity 1 algebra, the only thing you need is first of all, you have a base manifold and a graded vector bundle, finite dimensional graded, each one is a finite dimensional graded vector bundle over this manifold M. But then the degree is a positive graded. So L1 is degree 1 up to degree n. So you are not allowed to any negative degree and positive graded. And so on each fiber, that's infinity 1 algebra, infinity 1 algebra. So you have a bunch of a bracket here and satisfy this co-derivation. This is just graded Jacobi identity. And d lambda, so all those you can think of each fiber is strict to each fiber, and that's co-derivation, and square equal to 0. So that is just the, and then you just, so basically you each fiber, fixed point of m, and you have an infinity 1 algebra. And you want this infinite algebra structure smoothly patching together. Yes?
You did mention this book of Joyce, in which he also has the definition derived down.
He called D manifold, right? So so what, maybe Yunjin can answer the question. What?
I think they're very complicated. It's not an infinity category. They're sort of.
I mean, M in this story isn't a manifold, right? I mean, it's
No.
Derived manifolds are something you get by like maybe cutting nuts. Singular way, and then you have
Sorry, I don't remember.
I do.
Like an algebraic geometry with derived scheme, right? It's something which fixes the fact that your scheme isn't actually non-singular, right? And so it includes its goodness and extends it to thereby general possibility. Well, why are you assuming M is a manifold?
Sorry, what is your question?
I think it's just the idea is you have manifold separated with some stuff that allows you to have a category of fiber objects. And there are different ways to create this category of fiber objects.
But I do. I noticed Joyce have a paper D, but I'm not sure if that what. That's like 1,000 pages or something, and I do not know what is really the definition of D manifold. You probably read, Yunji knows much better, and I think he used the symphony ring, right? So basically, our idea is not to use the symphony ring, and the opposite what the Yunji wanted to do yesterday. I'm sorry. Yes. Yeah.
One example of this section is where M is just a manifold, you put it in the vector bundle, and the vector bundle has a section. And we think of it is that this situation models the zero locus of that section.
All right. So Rail basically talked about the example which I'm going to talk about. Yeah, exactly. I don't. But Chris, what is your question again?
The zero locus is smooth or not smooth?
No, not smooth.
So what's
M is just you just smooth manifold. For instance, like the case like what you're interested in. This is the most examples, like DF. Yeah, so DF with 0 sections, right? And that's probably the most. This is examples. And so yeah, that's this one. And this is exactly one of the special case. Any other questions? And now what is so you just need to unpack, which I talked about infinity 1 algebra point-wise, because what I talked about is really linear algebra, which I wanted to actually try to use derivation, but I was too tired last night. I just copy-pasted some slides yesterday because I really co-derivation is hard to but if you're interested, I'm more than happy to discuss with you and using derivation. It's really easy because we know all the linear algebra, algebra, Chauvet differential, all those things. It's very easy to look at that point of view. That's how I learned all those. So co-derivation is very confusing, but I was not able to have energy to to write the slides for that. But anyway, you have a morphism. What is morphism is just on the ambient space, Bayes manifold, just a map, and you have a bundle of those. Now you have basically what the morphism. So if you do not think of infinity one algebra, only ambient space, only manifold. So what does it just m prime, and you have a vector bundle. The only thing is you just allow yourself to think of a vector bundle as z-graded and positive graded, not the usual vector bundle, have a degree. And then this is just a map. Now the map here, I want to put in a phi here. And so each restrict to each fiber become L restrict to M. This Fm. And this guy is just the infinity morphism. That's all you need. And so each fiber, when you freeze each fiber, and that's infinite morphisms, which I talked about. And everything is just linear algebra. And fiber-wise, you need a patching them together. So that's just the morphism. This is a morphism. And the degree reason you can see, you only need to deal with finite lambda, because all infinite algebra, when you say infinity one algebra, normally you can have a bracket to infinity, but in this case, it only stop because all the vector spaces are positive degree. So everything is, and also phi k stops. So everything is a linear algebra, in fact, if you allow yourself. When freezing each point. So here's a few relations again. And now what is the lambda zero? Lambda zero is exactly, you can think of what is exactly, you start with L, and lambda zero is just a section. That's normally just the intersection. You talk about intersection. So that's very important to have lambda zero. But then if you allow only lambda zero, that's not it because you have to push it down. So that's why you got a different degree. And then this is a lambda zero is a section. Lambda one is a degree one bundle map. Lambda two is degree one bundle map from symmetric to here, and lambda three. So L1 infinite algebra avoids all kinds of degree. So all the degree become degree one. So that's very good. Compared to the infinite one infinite algebra. Infinite algebra have all the degree confusing. Here's everything degree one map. So this is a high bracket. So this is just two bracket. This is degree one, and this is a few relations. You can see this is a relation here. And morphism. So a few relation morphism. You have a map of phi one mapping lambda zero to lambda zero prime. You can think of lambda zero is just section of a vector bundle. You map this section to the other section. This first relation, and the second is a compatibility condition. So, and one example is this example, which this one's obvious. Usual manifold is. Let's look at this manifold. This is what Rio was talking about. If this vector bundle only has one vector bundle, degree one, L1, and then lambda zero is just this section, So this is one of the special case. And then what is morphism? You can see just if the intersection of lambda zero, if lambda zero prime, what is a morphism? This is what we call quasi-smooth. A quasi-smooth derived manifold is exactly just a vector bundle, only have one component, of a degree one component, the vector bundle. You don't have a higher. And then this exactly lambda zero. Just this example here, you have to put in this guy is degree minus one. Put in degree one. This is and then this is the exactly just quasi-smooth. And this is just a map. A map is just means you have this commuting diagram here, which is section mapped to the section. So that's what the rail was talking about, is this example here. Well, there's a DG point of view, which I have 10 minutes, so which I really like. So when we talk about the smooth manifold, what we do in graduate school, what is smooth manifold is locally, you tell you what it looks like. And then you have all the charts, all those things. And this is the one way of doing this, is similar things. So locally, what is the DG manifold? What is Z-graded manifold? Is a local model is basically locally is you have a base manifold M, and you have a sinfin function on the base manifold. On the fiber, you take the polynomial function on V. So, and V is a fixed graded vector space. So on direction on V, you take a polynomial function. On the base, take a sinfin function. And so this is just basically what the graded manifold, and well, one way of saying this is a sheaf, but you don't really have to think of a sheaf, which is graded vector bundling vector. This Butcher-theorem, which tells you. And what the DG manifold is just a graded manifold equipped with a homological vector field. A degree 1 vector field satisfies Q bracketed with Q equals 0. Q is that. So here is actually you don't have to use a sheaf, because here I'm looking at the sheaf of algebra of OM algebra, but everything's smooth. So you can look at global section. So in fact, Q is just really the global section derivation of the function. So just forget about the sheaf. That's also confusing. I would avoid it. This is my favorite example. This is how I learned infinite algebra or infinite one algebra, because we all know Chevalier-Allenberg differential, right? So if you look at Lie algebra, so if you look at G is a finite dimensional Z-graded vector space, and by function, because the vector space, when you think of a sinfin function, it's not sinfin function anymore. It's just polynomial function. So polynomial function just SV do, right? So SV do. So D is just a map between Q, the degree 1 derivation here. If it's derivation, because SG do is generates by GV, right? That's the generator. So the derivation, all you need to know is what component mapped to here, what this is, and looking at what this is. But in order to see, so the derivation is determined by this map here. But this one, you have to see what this is. This is you can just look at each component and look at the degree or the k, so you can get like a degree 0. Well, no, this is a weight called like a 0, 1, 2, 3, and that's how you get all the map. That's how the high bracket. So exactly. So this is, if you're giving G is a Lie algebra, this is just the Allenberg-Chevalier differential. Allenberg-Chevalier differential Q. And here, the only thing you need is just allow yourself to allow Z-graded. All right, so morphism is just means you preserve the Q. It's just that you have a DG manifold, you have single vector field. So if you're geometer, the easiest way is to think of two manifold, Z-graded, you have a 2 vector field. You map one vector field to the other vector field. That's it. When you write on the axiom, exactly, that's all the infinite morphism map. And that's all that's what I normally do. So, let me see. Oh, no, sorry. This one. So, yeah, I'm sorry. Yeah.
So suppose in this previous example, you take a section of the vector bundle which is transverse, the 0 section. And so that cuts out a smooth manifold, right?
Right.
Is that equivalent to the total space of the vector bundle equipped with this element?
That is a weak equivalent. Yeah.
But then you have a map going in one direction, right? How do you get the map going in the other direction? So the 0 set includes in the total space, right?
Right. But this is a weak equivalence. So you ask how to go the other direction, but then you probably have to use factorization, which is non-trivial. So yeah. So how the other direction, basically inverse, then you need to go all the way, yeah. So basically, one way of thinking, what is a DG manifold? That's how I define the graded vector bundle with a lambda, a bunch of infinite bracket. The same thing as the DG manifold with a positive amplitude. Basically, all the degree are positive. So in some sense, if you're interested in graded manifold, you can have both direction, positive and negative direction. A negative direction takes care of stacking singularity in some sense. If you look at the -1 is like a Lie algebroid, and -2 will be Lie 2 algebroids, and so on. So if you allow all the negative degree and positive degree, you probably you take care of both degree in some sense, both singularity. Here is just the intersection singularities. All right. So I talked about what is object? What are the objects? Objects here, let me summarize what are the objects here. It's just graded vector bundle with positive degree, each vector positive degree. And that's the object. Morphism is infinite morphism fiber-wise. That's the object. That's the object and morphism. So I need to define what is a weak equivalence, and I need to define what is fibrations. And then I should be able to finish my talk. So that's very simple. So the easiest way, what is a weak equivalence, is you look at, so what the tangent complex is, giving this a graded vector bundle, most important thing, you have lambda 0, because you have a bunch of lambda here. So you have lambda 0, it's just a section here. And you have lambda 1 and so on. So lambda 0 is a section, and now you take the derivative of this section, tangent map of this section. You get a t to the tangent map of lambda 0 of L, and then you can decompose this into, if lambda 0, so you have to look at 0 locus, sorry. Z lambda 0 is just all the point x. Just you want to look at the intersection here. And you look at the tangent map at this point. So the tangent map, and then this tangent space you can decompose as two parts, right? Because this is the intersection. So the tangent direction on the tangent bundle and the fiber direction. A fiber direction vector space is L1. So you can project to L1. So the tangent map, you get a Tm to L1 map. And now you just putting them together, one can easily see this is a chain complex. This is a cochain complex. This is called tangent complex. So very simple. And L1, just L1, L1, L2, and so on. L1 is just restrict to each of the L1, each fiber, and then just taking tangent. So this is a tangent complex. So a morphism induces a cochain map. So what is the weak equivalence? Exactly, just you require, this is a quasi-isomorphism. So you want a morphism between these two vector bundle. First of all, have to induce bijection on the classical locus, basic 0 points of a two intersection. They have to be the same as topological space. And then on each of this point, you require this tangent map to be quasi-isomorphism complex, which I mentioned. And that's weak equivalence. And then what is a fibration? Well, fibration should be just exactly submersion. You have a graded vector bundle, you want a submersion of this. So if you unfold the submersion, and then you will see exactly the base manifold have to be submersion on the vector direction has to be surjective. So if you're geometer, you really just want it to be two map of graded vector bundle map to be submersion as usual manifold. And then you can see it's exactly just the base manifold, submersion fiber surjective. So the theorem basically says this is a category fiber object, which is the proof requires is you need to use infinite dimensional AKSZ technique going to the infinite dimension space and using homotopy transfer to the finite dimension space to do the factorization. Basically, we prove the factorization theorem. And so I'm going to skip this. And I did prepare this, then you can talk about what dimension is. I think I'm running out of time. What is the dimension of derived manifold? In particular example, which Ray was talking about, only have one intersection of one section. The derived dimension will be dimension for M minus rank of a vector bundle, which makes sense, right? If you have intersection, transversal intersection, in this case, the dimension exactly should be the same, should be given by this formula. This formula gave you the right dimension. So, and so you can talk about what the dimension of a derived manifold. And the last thing is I'm going to just leave, I upload the slides in the, well, sorry, you uploaded for me. So I just, maybe they are, but okay. But anyway, so I'm going to skip this part. And this last, it just tells you how to take a fiber product. I gave you one example, how to take a fiber product for the usual manifold, going to the very easy way. If you follow this, you can see how the fiber product works. So since I'm running out of time, I'm going to jump to slides.